Okay, so we are on day 2 of thermochemistry, and what I'm going to do is I'm going to kind of follow along with the PowerPoint, so it would be really helpful if you guys would have the PowerPoint in front of you so we could kind of go through it together. But you'll notice that what we're doing today is talking about the difference between exothermic and endothermic reaction. Now you guys know the thermic refers to heat, to temperature. So exo, out, endo, in. That's the easiest basic way to think about it. So let's start with our exothermic reactions. Our exothermic reactions are where we have energy being released, often as heat. So my surroundings are getting hotter. If you let yourself, this can actually get confusing even though it's very simple. So think about it. There's a little drawing on the PowerPoint that might help you. If this is my system, okay, so this is where my little reaction is taking place, right here. An exothermic reaction means my reaction is giving off heat. It is producing heat, and that heat is leaving. Therefore, my surroundings over here, above, below, everywhere, these are going to get hotter. That's exothermic. If this system was a test tube, you would feel the heat leaving the test tube going to your hand as you were holding it. So my Q value, that's my heat, or my delta H, my change in enthalpy, those are going to be negative numbers for my exothermic reactions. Logical, because if my system is starting with 500 joules of energy, and then a lot of that energy is leaving, I'm going to end up with less. So it is a negative change in enthalpy. Okay? If I go from 500 to 100 joules, to calculate my change, I do what I ended with minus what I started with. So we make that a negative value. The other option here is your endothermic reaction. But before we get to that, see, I almost got myself in trouble again. Let's go back to your PowerPoint. One of the other things you see in your PowerPoint is a graph. If you are doing a graph of an exothermic reaction, you will see that your graph is going to go down. Okay, the energy is being released. So if this is my energy over here on the side, if my reactants are here, I'm going to go down through the course of this reaction and end up with my products down here. So there's my reactants, there's my products. I have clearly lost energy, and this would be an exothermic reaction. Okay, exothermic. The other way you can see it is with an equation, and you'll have your energy written with the products because the energy is being produced. Don't overthink this, okay? The other thing I'll tell you is I don't care what happens in the middle of that graph. If I start here and then I go up and then I come down and then I go up and then I actually go backwards and I make a couple loop-de-loops and a little bit of sort of a smiley face looking thing up in here, and then I do a squiggle, it looks like Bart Simpson's hair, and I draw a heart and I end up down there. Whew. First of all, if you ever get a graph like that, man, you screwed up. All I care about is I started here, I ended here. That is an exothermic reaction, when I start higher than what I end. Now, let's jump to my endothermic reactions. Endothermic reactions are taking in heat. Okay, the heat is being brought in. So again, if this is my system, okay, this is where my reaction is happening, if it's endothermic, that means the heat is coming in to the system. So my surroundings are actually going to get colder. Now this is the one that can mess with your head if you're not careful. If your system was a test tube, okay, there's my system, then if it's pulling the heat in from my nice little hand, okay, which is surrounding it, and no, I'm not even going to try to draw a hand, I'm going to feel cold because the heat is being taken from my hand. That is going to be a Q or a delta H that is positive. Okay, we are gaining heat into the system. It is positive. If we continue with your PowerPoint, we can also graph this, or we can write it as a reaction. If you write it as a reaction, then obviously your energy is going to go with the reactant since it's going in. As you graph it, if I start lower than what I end, here's my energy, this is my reactants, this is my products, this is going to be an endothermic reaction because I end up with more energy than what I started, I have taken it in. So again, I don't care what your graph does in the middle, okay, whatever kind of loop-de-loops are going on, okay, as long as it ends higher than where it starts, you have an endothermic reaction. So let's go to something you're familiar with. One of the things you guys are very familiar with at this point is the phase change diagram of water. Solid, liquid, gas. Okay, and then you know that freezing and melting are here, okay, and you know that vaporization and condensation are here. Well, if you look at this graph, you can think of it in terms of endo and exothermic. Now, this, believe it or not, is tough for people. For example, if I ask you about melting, is melting endothermic or exothermic? Lots of times we do just fine and we say, oh, well, that's endo because to melt something, you've got to put heat into it. Piece of cake. If I ask about vaporization, oh, that's endo. I can do that. Piece of cake. Got to put heat into it. But what you have to remember is that you can also see it from this graph. Here's my starting point. Here's my ending point. That graph is going in an upwards direction, so as I go from solid to liquid, that's endothermic. As I go from liquid to gas, that's endothermic. Where it gets tougher for people is the opposite direction. Condensation is an exothermic process. In order for water to go to gas, from gas to liquid, you have to take the heat out of it. The worst one, okay, so this is my condensation, is the freezing. Okay, freezing, believe it or not, is exothermic. And I know that's killing you because you're like, the ice is getting colder. Like, there's no way that's exothermic. It's getting colder. But what you have to think about is what your freezer is doing. Your freezer is absorbing the heat, or actually sucking the heat out of the water to allow it to go down here to solid again. Okay, that's what's happening with freezing. So again, I start here, I end here. That graph is in a downward direction, which, as we learned, is exo. It is perfectly fine, by the way, it is perfectly fine when you draw this graph if you want to just draw the exothermic part in reverse. Solid, liquid, gas, okay, and say, okay, liquid to solid, that's going to be my freezing, and then gas to liquid is my condensation. Now I can see that it's exothermic. It's all the same as this. It's just a matter of how it looks better for you. So, the next topic of today is something called heat capacity. Get a new screen up here, okay? Heat capacity. Heat capacity is abbreviated, the abbreviations in this chapter, with a little c, and it's how much heat it takes to heat an object by 1 degree Celsius. We kind of touched on this a little bit with calories, okay? But heat capacity, how much heat does it take to take whatever it is by 1 degree Celsius? Clearly, the identity of the substance matters. Water and sand is my best example ever. You go to the beach, okay? You got water, you got sand, all right? Look, water. Oh my gosh, this is horrible. Sand. So if it's beaming down 90 degrees outside, that sand is going to burn your feet, that water is not. It's because of the heat capacity. Water has a different heat capacity than sand. Water changes temperature very slowly. Okay, and we'll get into this a little more later in the PowerPoint, but we say it has a high heat capacity because it really can handle a lot of heat before it goes up by that 1 degree Celsius. That's why you can walk in the water and it's relatively not that hot. The sand, on the other hand, okay, the sand is kind of difficult because when you're walking in the sand, dude, that stuff changes temperature so fast. So the sun beaming down on it, it is getting hot. And so it has a very low heat capacity. So in terms of chemistry, you know we love our little moles. So you will see different versions of heat capacity. One version is called the molar heat capacity. Molar heat capacity is we're trying to adjust for, we can't adjust for the identity of the substance because that's just, it's going to vary. But we can certainly adjust for the amount. The amount present obviously matters. Heating up a pan of water versus heating up an ocean, totally different. But molar heat capacity, we're adjusting for the amount. We're going to say how much heat does it take for 1 mole to go up by 1 degree Celsius. So the formula we've got, Q equals NC delta T. The N is the number of moles. Kind of makes sense. Okay. Your C is your molar heat capacity. And your delta T is your change in temperature. Okay. Take your final temperature, that's an N, I swear, minus your initial temperature, and that will kind of show you how your temperature is changing. Truthfully, we don't use this a lot in chemistry. The reason we don't use it a lot is because we don't really measure things in moles. Instead, what we deal with is we deal with specific heat capacity. Same idea here. We can't control for the identity, but we're controlling the amount. Except this time, we're not doing moles, we're doing grams. So specific heat capacity is taking 1 gram up by 1 degree Celsius. And again, you saw this formula on the lab that we did in class on Thursday, if you were here. The formula is Q equals MC delta T. Again, Q is the heat, your M is going to be your mass, your C is your specific heat capacity, and that's going to be given to you in almost every circumstance. And then your change in temperature, you take your final temperature minus your initial temperature. So that could be a positive or a negative number. Now, the only time your specific heat is not given to you is with water. You're expected to know that water has a specific heat of 1 calorie for gram degree Celsius. That means it takes 1 calorie to do 1 gram, 1 degree Celsius. Or if we switch that to joules, it's 4.186 or 4.184. I swear it depends on where you read it. Joules to do 1 gram, 1 degree Celsius. So the water one that you need to know is this 1 calorie one. Don't worry about the other. Okay, so if you look at your notes, you've got several practice problems. Notice a couple things. You don't have to change it to degrees, you don't have to change it to Kelvin. Degrees Celsius works just fine. Sometimes you're not given the M and the C and the delta T. Sometimes you're given the Q and the M, and you got to find the final temperature. So just kind of look through those, make sure you understand what to do with them. The last little part of this is how do we apply specific heat? Why do we care? What do we do with it? So in your PowerPoint, you'll see the conversation about walking in water or sand. The first law of thermodynamics, which I'll let you look at. I won't waste time on that. The thing that I want you to see, the last thing for today, is calorimetry. This is what we're going to be doing in Monday's lab. Calorimetry is a way to use the specific heat to actually figure out how much heat we're producing because we're using a device called a calorimeter. Basically what we do is we take the temperature before the reaction and after the reaction, and we use the mass of whatever it was with the specific heat to see how much heat was actually being created. Your PowerPoint has got a great diagram of what's called a bomb calorimeter. Those are big and fancy and expensive. And then, welcome to my world, the coffee cup calorimeter. Either way, it doesn't really matter. The very last slide in the PowerPoint, you'll see calorimetry involves MC delta T, just like before. Because the idea of every calorimeter is I have a sealed container, okay? I'm going to have another container inside where my reaction is happening. The idea is that any heat lost by the reaction is going to be gained by the water. So even if I can't measure the heat in that reaction, if my water goes from 10 degrees to 50 degrees, then I know that reaction must have produced 40 degrees. So we're going to get into that on Monday. You're actually going to see that in action, but this gets you a little caught up from Friday. Hopefully it helped.